So we're going to continue what we started yesterday, and what I'll talk about today is, again, going to work with my students, Jayadev Acharya Ashkan Jafarpur, who is here, and another Tirtha Suresh, we call him Tirtha. He's done most of this particular work. So just let's remember what we did yesterday. So we said that if I want to estimate, if I have a coin and I want to estimate the bias of the coin, the probability of heads, then I take n samples and I'll be off by square root of n, roughly. I'll get the mean plus minus square root of n. I normalize by n, so I'm off by 1 over square root of n. So if I have n samples, my error of my estimate is about 1 over square root of n. And if and we're interested in estimating distributions now of a large alphabet, not alphabet of size 2, but alphabets like English, alphabet that are large, like 500,000. So we have a distribution over k symbols. And then we said that the L1 distance behaves just like it did with the binary case, 1 over square root of n, except now it's like square root of k over n. Okay. So when you look at it, you see, already you see that this is bad. That's why it's in red. Because first of all, you see that the number of samples has to be at least k, at least the alphabet size, which is very natural. If you have an alphabet size 1 million and you see less than 1 million samples, definitely cannot expect to estimate the distribution. But furthermore, it goes like down after that, like 1 over square root of n. So which means that if we invert it, we had this like insane measure of the sample complexity. So if you want to get to within delta, then you need something like 1 over delta squared. And that goes very fast. So then we said that's a problem, and so different groups, ours and others, have been trying to address this issue, and there are 3 main approaches people have taken. One that we discussed last time was to add a structure, to assume that this distribution cannot be any distribution, but maybe it's monotone or M-modal or something like that, okay? So we said, for example, if you add the assumption that it's monotone, then the number of samples, you can reduce it from k to log k. There's a small loss here. Instead of square root, it's you'll get like, it goes down instead of square root to 1 of the cube root of this number, but you'll get at least log k instead of k. So there's an improvement here, and so this is one approach to make assumptions about the distribution, and the approach that I want to discuss today is what we call out of the durable. So like maybe we modify a little bit what we want to achieve. Maybe it's still close to what we want, but a little weaker, and then we see what we can get. And so that's what we'll discuss today. So no assumptions. We're going to look at all possible distributions, but we'll see what we need to modify in order to get some results. So we'll look at what's called combined probability estimation. So okay, so that's where we are. So every estimator, every natural estimator that you can think of, will assign the same probability to all symbols that appear the same number of times. So for example, suppose that you have a distribution over the first 6 letters, A to F. And let's say you took 5 samples and you get CA, CDA, right? So for example, F is okay. And then A and C both appeared, hopefully you can tell the difference, this is brown and red. A and C both appeared twice. So any reasonable estimator that you'll come up with will give the same probability to A and to C, right? These are IID distributions. There's no way for you to give a different probability to C than to A. And B, E, and F did not appear. So whatever probability you give them, it could be 0, but it could be non-zero. But whatever it is, it makes sense that you'll give them the same probability. And all natural estimators behave that way. Any estimator that you can look at will behave that way. And you can also rigorously justifiable, because if you see something like that and you give a different probability to C and to E, then you can look at any permutation, and you'll be, for some of them you'll be lower, for some of them you'll be higher probability. And because the distance all these distances people look at are convex, then you'll be making a bigger error in a min-max sense. Okay, so it's rigorously justifiable. So we talked last time about insane measures and sane measures. So this is, if you do anything else, then I would say you're back to being the insane. So any estimator will have this property that it assigns the same probability to all symbols that appear the same number of times. Okay, so if that's the case, then we may as well combine the probabilities of things that appear the same number of times. So we look at the combined probability of all symbols that appear any given number of times. So to be a little more precise, let's call mu, that stands for multiplicity, with the number of times that a symbol has occurred. And n mu be the number of symbols that appeared mu times. And then S mu, I'll give you an example in a second. S mu is the sum of all probabilities that appeared mu times. So for example, again, distribution over A up to F. And let's say you took 4 samples and you saw A, D, C, D. Okay? So N0 is the number of symbols that appeared 0 times is 1 because it's just B. Just a second. Yeah, B did not appear. And 1. Just a second.
Shouldn't have.
Yeah, so I apologize. This is the distribution over A, B, C, D. Yeah, sorry. So B did not appear. N1, the number of symbols that appeared twice is A and C. Okay. N2, the number of symbols that appeared twice is 1, just D. Okay, so it's a distribution just over A, B, C. Apologize. Okay. And so these are N0, N1, the number of things that appeared 0 times, once, twice. Okay. And if you look at S0, the total probability of things that appear 0 times is just the probability of B. We don't know it, but it's that probability. And 1 is the total probability of things that appeared once, so it's PA plus PC. And N2 is going to be just PD. S2, sorry. It's just the sum of the probabilities of the things that appear twice. Okay. So these are the sum of the probabilities. Now, if you want to estimate the individual probabilities, the only logical thing that you can do, as we said from the previous slide, is just divide this total probability, and this is what you're looking for. It's just the normalized probability. So QA, so your estimator is going to be, if you want to assign the same probability, you estimate a Q. P is the actual probability, and Q is going to be our estimator. So QA is going to be equal to QC, and that's what you want to be S1 over N1, which is S1 over 2. And ideally, you want, similarly, QB is going to be just S0 in this case, and so on.
Okay. Is S the estimate, or is S the probability?
No, S is the total probabilities. P's are the total probabilities, and S is the correct value, so it's PB, PA plus PC. That's what you're trying to estimate, okay? And what I'm saying, suppose you have some estimate for this, for S, then the only logical thing to do is you'll take whatever your estimate is, let's call it S hat, and divide by this. But this is what you want to get. This is ideally what you want. Yeah, but I agreed it's a little bit. Okay. So S0 is, in this case, is the probability of things that you have not seen. So that S0 is the probability of things that you have never seen. Okay. All right. So the combined probabilities are just S0, the total probability of things you have not seen, total probability of things you have seen once, and so on, up to the probability of things that you have seen n times. Okay. And your estimator that you'll come up with will be E0, your estimate for 0, and so on up to En. Okay. So again, you need to estimate to quantify your distance between your estimator and the true things. So we just do the same thing. So if you have S0 hat up to Sn hat, you estimate of S0 up to Sn. Then we'll look at 2 distances. One is the L1 distance, just add up the absolute values of the differences. And the other one is the KL divergence. It's the summation of the real things times log of S divided by S. So what we're going to do is we're going to try to estimate the total probabilities, the summation of probabilities of things that appeared once, twice, and so on. And then if you want to estimate the individual probabilities, then like we said, you're going to normalize. Okay. So let's see what empirical frequency does. So suppose you've seen a sequence of length 9 symbols, and this is the sequence. So you have 2 symbols that appear twice, A and B. So the total probability of things that appear twice is PA plus PB. Okay. And what probability will empirical frequency assign to things that appear twice in this sequence? So you have a length 9, so to A it assigns probability 2 over 9, to B it assigns probability 2 over 9. So it will say that the total probability of things that appear twice, empirical frequency will say 4 over 9. Okay? Very natural. And just reminding ourselves that n mu is the number of things that appeared mu times. So the total probability that empirical frequency will give to things that appeared mu times is going to be to each one gives probability mu over n, and n mu of them in this case too, so we multiply by that. Okay. So, so the question is, for example, if you want to ask how many samples you need to get to L1 distance of at most 0.1 with some high probability, then you notice that empirical frequency, to 0 it will always give 0 probability, right? Because you say what total probability does empirical frequency give to 0? It's going to be 0 over n times the number of elements that appear 0 times. In reality, maybe you don't even know what this number is because you don't know the alphabet. But whatever it is, if you know the alphabet, you multiply by 0 till you get 0, okay? So, so empirical frequency always gives 0 to things that appear 0 times. It's a big problem. So take a uniform distribution. So we're trying to see how many samples you need if you want to estimate the L1 distance between the total probabilities to at most 0.01, probability which is at least 0.09. So, so suppose that you have a distribution of 1 up to k, and suppose you took a little less than k, like 98% of k, okay? Then S0, then there'll be at least the probability of things you will not see is at least 0.2. There could be repetitions, in which case it will be bigger, but it will be at least 0.02. So S0, the total probability of things you will not see is at least 2%. Right? I have a distribution of size k. I take 98% k samples. There'll be at least 2% of the symbols that I will not see, maybe more. The total probability, because it's uniform, is at least 2%. So that means that if I want to estimate, but the actual value is that empirical frequency gives is 0. So that means your distance is going to be at least 0.02. Okay. So if you want to estimate your distance, which is less than 0.01, you need more than 0.98 k. So you need at least that. Okay. So what this shows us is that, this measure that we have when we are looking at estimating not just the individual probabilities, but the sum probabilities is still non-trivial. Like in this case, I want to estimate those combined probabilities to within 0.01. I still need the linear number of samples. Okay, at least this doesn't. Is that clear to everyone? Yes.
How is this different from directly computing the empirical probabilities?
So the thing is this, that we're trying to make things easier for us. So we know from the previous thing that if you want to estimate the individual probability to an L1 distance, okay, we get square root of n over k, right? So square root of k over n. So, so n has to be at least linear in k, right? Because if as to go,
probabilities can be estimated with higher reliability.
Right. So what we're saying now is we're trying to make the problem a little easier for us. Maybe you'll say it's a lot easier for us. Maybe we can discuss. But so instead of estimating the probabilities of individual elements, so let's say the sequence here is A, B, E, B, C. So you might give the probability of A and the probability of B. And then you look at the distance. What we're saying is this, that for A and B, you're going to give the same probabilities anyways, if you're any reasonable estimate. So let's combine the probabilities and see how well you do on the combination of those probabilities. That's a little easier because maybe within them there's variability. So we're just trying to estimate the total probability, and that should be a little easier than estimating each one of them. Okay? So what we're showing here is that this doesn't trivialize the problem. If you tried empirical frequency, the number of samples you need is the same, it's still linear. Maybe you get different constant, but it's still linear. So is that okay? Right. What good Turing does is,
and I guess one question one could ask here is, this is for overall distributions, right?
Right. This is for the worst.
Distributions where this will be tight will be distributions which will generate some things once, some things twice. That will be like the worst distribution.
Correct. Mm-hmm.
So do we know what the worst distribution is?
For this particular one, yeah. I'm not assuming. Okay. So first of all, we haven't said what the We haven't said what the estimator is and so on, right? This is for empirical frequency.
Oh, I
We're
see.
just saying empirical frequency doesn't help you that much.
Oh, I see. But you could do much better.
Well, that we'll see.
Okay.
So, so your S2 there, I mean, you're drawing from the underlying distribution. And based on what you draw, I mean, your S2 values are random.
Right. So that's right. That's right. So it's kind of funny. So beforehand, you estimated the probability of A, the probability of B, the probability of C. Now you're estimating the probability. What you're estimating depends on what you have seen. If
How many things?
correct. So for example, if now A appeared twice and B appeared twice, then S2, the probability of things that appear twice, is going to be the probability of A plus the probability of B. Next time you'll try, there'll be other things that appear twice. You'll be estimating something else.
And our goal is to not estimate all the individual frequencies, but just try to get these things.
Correct. So we saw last time, we saw that if you try to estimate all of them, that's impossible. The best that you can get is square root of k over n, which we said because you have square root, like 1 over square root of n, so it grows like square of whatever distance you're trying to estimate, which is large. Yes.
Yeah, this one also seems funny because just of what you said, the more samples you take, the more likely you're going to have different categories, right?
Correct. But it makes it tougher, that's true. But what if that is correct, that's the direction I would like to hear, to say that this is a tough problem. But if you try to make it sound easier, then imagine that you have a distribution over size k, right? Then if you try to estimate the distribution itself, you need to estimate k parameters. There's p up, right. Here, no matter what the size of the distribution is, you'll estimate the probability of things that appear at 0, 1, up to n. So you're trying to estimate at most n plus 1 parameters that's independent of k. The number of parameters you're trying to estimate is independent of k. The point is that according to what we believe in, after looking at this a long time, that's the most you can do anyways. Because if things appear twice, you'll give them the same probability if things appear 3 times. So there's no reason to try and distinguish between things that appear twice. You're just guessing. So this is what you should be looking at. And what we see here is that even though we're trying to estimate only n parameters, regardless of k, even if k is a trillion, but our sequence length is 100, we'll try to estimate 101 parameters, 0 up to 100. Still, the number of samples you'll need is proportional to k. That's what it's showing. Yes.
Since S0, S1, S2, and so on, these are all disjoint in the sense that the A, B's and all.
Yeah, they have to.
Actually estimating just K parameters, right?
Why?
Because
When you say just, I'm thinking of k as being very large. I'm not expecting the word just.
sure, yeah, but so if n is the number of samples, you have S0, S1, S2, and so on.
Right.
But some of them, so since they are disjoint, the total number of non-zero things here can be at most K.
Actually, I would say even square root of k. That's even lower, right? Because so that's a good point. So what he's saying is, he's saying, mind you, I'm thinking of k. I'm thinking of the other regime where k is very large because I want to say you can learn with few samples. But ignoring that, he's saying that you're looking at S0 up to Sn. He's saying the number of SIs that can be non-zero is at most k. But in fact, it can be at most square root of k. And that's because you could have maybe S1, S2, and so on. If S1, the things appeared once, and things that appear twice, and so on. So you can have at most square root of k of them before you get to k different ones. Okay? Yeah, so that's true. So at most square root of k of them will be non-zero. That is also correct. Sorry?
But another related question is, if you made some assumption on the distributions, you would be most things would appear, once or twice or three. I wouldn't expect, you need some distribution that favors some things quite high. So you need some really strange power law, maybe distribution to see square root n things, right? Square root k, k square root n things.
Yeah, you might, right. But last time I was, there were friendly questions that says, why do you make assumptions on the distribution? Who knows the distribution is monotone and so on? What we want to do here is make no assumptions on the distribution. And you're right, that maybe typically you'll see fewer multiplicities. Okay. So empirical frequency we see requires a number that is proportional to k, and now remember our job is to try to get this number below k. That's all our struggle, everyone's struggle in the last 10 years is try to see things that will give you the number that you can estimate distributions with less than with fewer samples, definitely fewer than linear. Okay. So, so good Turing. So n mu, remember, is the number of symbols that appeared mu times. So n mu plus 1 is the number of symbols that appeared mu plus 1 times. And the good Turing estimator, what it does is for mu, number of multiplicities between 0 up to n, the probability that is assigned to things that appeared mu times is the number of things that appeared mu plus 1 times mu plus 1 over n. Okay? So if you want, you can think of it. So empirical frequency will assign its probability, which is mu over n times n mu, right? Mu over n to each one, and then n mu. Good Turing. It's assigned to this one the same probability that empirical frequency assigns to things that appeared one more time. Right? So this is what we call E of mu plus 1. The empirical frequency assigns to things that appear mu plus 1 over n times n mu plus 1. So good Turing actually shifts in one. So we'll see in a second why this is actually a good estimate. Okay. So we'll show in the next slide that actually, if you look at the expected value of G mu is the expected value of S mu. So as you pointed out, S mu is a random variable now at this point. And the expected value of S mu is going to be the same as the expected value of G. So that makes it nicer. Okay. So in particular, what is the probability of the unseen mass of things that you have not seen? So empirical frequency gives it probability which is 0. And good Turing will give it the probability that E1, which is the n1, 1 over n times n1. Okay. And good Turing is very useful in natural language processing, so it goes back to Church and Gale started using it. And I think it's definitely one of the standard techniques people use for estimating probabilities. I don't know if you care about the motivation, but I guess now everyone's seen the imitation game, so I don't care. But the Germans had a password book that they gave the U-boat commanders, and they were supposed to choose passwords from this book, and they were trying to estimate the probability that they will choose passwords from different pages of the book and so on. So you can imagine you have a very large number of pages, you have very few samples, and you try to estimate what's the probability that this commander will choose from the beginning of the book, the end of the book, and so on. Okay, so what kind of performance guarantee? So we'll get that in a second. What kind of performance guarantee does good Turing give? But before that, I just want to show you this part. So that good Turing is unbiased. So okay, what I'll show you is remember we're looking at you have an ID distribution. You sample n times. The way we have looked at it, which has helped us simplify proofs, I think, significantly over what people have done before, is so they've looked at actually this exact problem. That I have a distribution, I sample it n times. But instead, what we're going to say is that you sample it Poisson n times. So this Poissonization is a technique that people have used. And so instead of saying you sample exactly n times, we say we'll sample Poisson n times, try to estimate the distribution. It makes the proofs a lot easier. Okay, but it's almost the same because sample Poisson n times, you can actually prove it. So it's not like there's no hand waving. You can show that the results that I'll actually present here will hold the same for Poisson, non-Poisson. It's just the proofs is easier. And the reason is because if you sample n times, then the number of samples is going to be somewhere between n plus square root of n and n minus square root of n. So it's roughly n anyways. So your estimate is almost correct. Okay. So when we calculate the expectations, this will come in. So S mu is the total probability of things that appeared mu times. We can write it as a summation over all symbols of the probability times the indicator function when x appeared mu times. Okay. Right? That's the definition of S mu. It's a random variable. So what is the expected value of S mu? We have to sum is the expectation of this. So it's the expectation of px times, I would say summation of the probability of x times this is the Bernoulli random variable times the expectation of that x appeared mu times, one of that, the indicator function, which is just the probability that x appeared mu times. Now, remember we are sampling things Poisson n times. And when you do that, you can show that each symbol, x, will appear Poisson n px times. So I have a distribution, p1 up to pk. I sample n times. So the number of samples will be Poisson n. And then if I look at the distribution of the number of times that x will appear, it will be Poisson n times px times probability. So, so the probability that x will appear mu times is just e to the minus npx times npx to the mu divided by mu factorial. So it's this summation. And then what we can see is that we have px here, which is kind of funny. So we want to kind of combine things here. So let's multiply here by n and divide by mu plus 1. So we'll get second. So okay, so get n mu plus 1. Okay, so there should be, okay, this is correct, still correct. Okay, so multiply by n, so get npx to the mu plus 1. And then you need to divide by n, so you get 1 over n. So this is okay. It's just 2 steps, so we could have done it by 1. And then multiply here by mu plus 1, and here by mu plus 1. So you get here, we'll get mu plus 1 over n. And here you'll get the probability that, that x appeared mu plus 1 times. So it will be mu plus 1. Okay, so that's this. Everyone agrees? Could have been written a little better, but it's okay. So, so what we get is the mu plus 1 over n times the expected value of n plus 1. So, and this is exactly the definition of this is the expected value of g mu. So the expected value of s mu is this is the expected value of mu plus 1 over n times n mu plus 1. So this is the definition of g mu. So we get that the expected value of g mu is just the expected value of s mu. Everyone is okay? Any questions? Yes?
Just to clarify something, what happens when mu equals n?
So, okay, so that's one reason why we're doing this way. So you're right that if you looked, and so if you're doing this, the analysis on the exact sequence length n, then you'll get something funny that happens at the end. In the sense that it will always be 0, right? The probability, but in reality, it's not a big deal because if things, in reality, what people do is they use good Turing for things that appeared few times, and they use empirical frequency for things that appeared many times, right? If you take 100, if your n is 100, and you see things that appear 50 times, you're not going to use good Turing. You know the probability is half. So you'll never use good Turing for estimating probability that are n. Okay. But if you're going to do the analysis, then you need to worry about these things. And that's what makes it more difficult, right? So that one of the things that make it more difficult. There's also dependency. If you take n samples, then the things that appear twice, then that number is not independent, depends on how many things appear 3 times and so on, because summation of all of those should sum to n. So this analysis actually gets rid of all of this. So there's no, in this case, there's no n anymore. For any, this analysis holds for any mu. Even if n is 100, this analysis will hold for mu equals 1 billion. Okay? Yes.
It is biased if without Poissonization, right?
Without, yes. If you don't, that's right. So if you don't do Poissonization, then it's biased. But this is correct. This is not biased, and this is yet another thing that helps us with simplified analysis. But they can prove it too because the bias is not that big, so they can prove the results as well. Okay. So this is so we show that the expected value of g mu is the expected value of s mu. Okay. So hopefully you see that this is nice. This is the simplest proof you will ever see. Even though I didn't write it in the best possible sequence. It's correct. Okay. So remember that if you try to estimate the whole set of probabilities, then you need a number which is linear in k, right? You need square root of k over n. And even if you try to look at the combined probabilities, if you do empirical frequency, again you need a number which is linear in k. So with good Turing, what would you think it will reduce it? So you want to estimate this combined probability to, let's say, 0.01. What would you hope? So, okay. So estimating the original probabilities was square root of k over n. Then you made the assumption, let's say, of monotone. Then it becomes like log of k instead of, and you have n, and then you have a different power, 1/3. Doesn't matter. Okay. So so now we're combining them. What would you hope for? What would you consider to be good? So I'm trying to estimate this combined probability to some number like 1%. What would you consider good? So empirical frequency, you can do it with linear.
Log K.
Log k. Any other bids? Constant. Okay. So yeah, that would be very good. And indeed it is. Okay. So it's a constant. So so in what I'll write here with high probability stands for probability which is 1 minus 1 over polynomial in n. So its probability is close to 1. And I'm going to hide polylogarithmic factors. So if I have n times log n, I'll just write n. So I don't care about the logarithmic factors. So what McAllister and Shapiro started looking at this problem, showed in 2000 actually. So this problem, a lot of people have looked at good Turing, but until 2000 they just had like some kind of hand-waving arguments why it works, but there were no proofs. Okay. So what they showed is that if you look at S mu and G mu, that they're off by at most some constant. There'll be some logarithmic factors of mu plus 1 over square root of n. So there may be another square log n. I'm sorry, log of n. So that's what they showed. So the nice thing about this is that it holds for all distributions regardless of support size. So we're trying to estimate S0, S1, S2, and so on. No matter what the support size is, you go off by at most this with high probability close to 1. So that means that if you give me a number of samples of 100, I can tell you how well I estimate this. And I don't care what the distribution is. The distribution could be of an infinite support. K could be infinity. I don't care. Given the number n, I know how close I am to the distribution. And so that's the good thing. It's also good when mu is small. So if mu is small, then you get 1 over square root of n. It's nice. However, when mu is bigger than square root of n, this is meaningless, right? Because you get these are probabilities that are at most 1. That's fine. So this therefore does. Remember, we're interested in looking at the L1 distance because we're looking at classification applications. So we'll look at the L1 distance. So if you want to show that the L1 distance goes to 0, this will not give it to you, because it will give you up to 1 over square root of n. That's fine. We'll sum to something, or maybe up to 1 over n. But then you need to sum things that could be 1. Okay. So it doesn't give that to you. So is that clear? Everyone is okay? So, so the question is, what happens when mu is bigger than square root of n? And Brook and Mansour in 2005, what they did was they combined. It's very logical. They combined good Turing and empirical frequency estimator. Let's call it C mu. And what they did was that if the number of samples is bigger than n to the 0.4, then they use empirical frequency estimator. If the number of samples is less than n to the 0.4, then they use good Turing estimator. And with that, they showed that the L1 distance is goes at most as like 1 over n to the 1/6, and then there's K divergence. Let's not worry about this. These results are always going to be the square of this. So there's the Pinsker inequality that relates L1 distance and KL divergence, and these results almost, I mean, they're in this case, they always go the way Pinsker inequality expands into go. So this will be roughly the square of that. Okay. So the nice thing is that you can estimate the distribution to L1 distance independently of the alphabet size. Okay, so that's the nice thing about that. So, but now let's just see. So let's see what it means. So, for example, if you want to estimate L1 to be less than 0.1 with probability, let's say 0.9, then you need at least, so you need roughly 1 million, right? Because this doesn't matter, but this L1 is going to be just 0.1 to the 6, so one of that will give you 1 million. Okay, so still there's something to be concerned about, right? So if you want to estimate the distribution to within L1 distance of 10%, then you need 1 million samples, and you may not have that much. As we discussed last time, maybe you're estimating things in a context of 2 previous words, so to get 1 million times this context will take you a lot of samples. So there's still more to be considered. So any questions? Okay, so then one could ask whether this is optimal. So the results that we derived, and like I said, it's mostly Tuta's work, but also with Ashkan and Jadev. So a few results. So first of all, you may want to ask whether you can improve good Turing and empirical frequency, this combination. So what does this mean? Could mean that maybe you take a different, they have a cutoff underneath. For things that appeared few times, they use good Turing. For things that appeared more times, they use empirical frequency. The cutoff is n to the 0.4. Maybe you can vary the cutoff. Or maybe what you could do is some linear combination, any kind of linear combination between the two. And the answer is no. No matter which combination of good Turing and empirical frequency, you can find a distribution P such that the difference between the L1 distance between the distribution and your estimate matches the upper bound that they had, 1 over n to the 1/6. Okay. Then you can ask whether you can find an estimator with better performance, something that will be better than this, and the answer is yes. You can derive an estimator such that with high probability, the L1 distance is not going to go like 1 over n to the 1/6, but 1 over n to the 1/4. Okay. So you're dividing by a larger number. And then you can ask whether this is optimal, and the answer is yes, that this is also a lower bound. Okay. And if you wanted to ask about KL divergence, then all these results will hold, the square of these results will hold for KL divergence. It's 1/3, 1/2, and 1/2. Okay. So you can just look, if you want, just look on the left. Look at the left. So basically, you can improve on the good Turing estimator. And the way to do it is, the reason good Turing helps you is because it reduces the biases. We saw good Turing was an unbiased estimator, but it has high variance. So you look at the difference between the value and what you estimate. So the expected value, the bias is 0, which is good, but has high variance. And if you want to reduce this result, then you need to come up with an estimator that has both low bias and low variance, and that's what this estimator is. Okay, so a couple of observations. So one is that it holds for any k and it's optimal. And then you may ask, like, so if you looked at the KL divergence side, which was here, then they got n to the 1/3 and n to the 1/2. You might say, okay, is it significant? So again, we can look at a sample complexity point of view, which we remember from last time, kind of accentuate things. So suppose that these constants are the same, but it's not like we've shown it, but let's assume that. So if you want to estimate things to KL divergence, which is 0.01, then good Turing and empirical, the combination you'll want 1 over n to the you'll have 1 over n to the 1/3 to be 0.01. So you need 1 million of these things. Okay. So whereas if you use our approach, then you need it just to be 1 over delta square, so 100 square, which is 10,000. So this number is obviously a lot easier to obtain, and also these things are computationally efficient and can be done in linear complexity. Okay. So, and you can ask, why do we care about good Turing? So that's we'll talk about tomorrow. We'll talk about classification. So you'll see that you can use this to get results for classification. So basically, what we've said is that here in this part is that if you If you want to estimate the whole distribution, then you need a number of samples which is linear in k. But if you just want to estimate the total probability of things that appear at 0, 1, and so on, then you need a constant number of samples. So you give me the estimate, like say I want to estimate 2.01, I'll find this n, and so just take this many samples and you'll be that close. I don't care what the distribution is. Okay, so it's kind of out of the doable, you can do that. So that's another approach, a second approach. I'll show you another example of this approach in a second, where we kind of relaxed the question that we asked, and then the number of samples went from k to just a constant. Anyone has any questions about this? There. Yes. So what I want to do now is show you yet another relaxation. So what we did now was we estimated, instead of estimating the actual distribution, we estimated the combined probabilities, probability of things appeared once, twice, and so on. And like I said, one can argue that this is the only thing you can do. If two things, if A and B appear the same number of times, the fact that they have different probability is a tree that fell somewhere in the forest. You'll never be able to tell. You've seen that they appeared the same number of times. The only thing you can do is just give them the same probability. And if you do that, then if that's what you're trying to do, then you can. Okay. So what I want to do now is go a step further and say, so I'm not just trying to estimate maybe the probability of things that appeared once, twice, and so on. What I'm trying to do now is just estimate the multiset of probabilities, to say that the probabilities are 0.5, 0.3, 0.1, without associating them with the individual elements. So I see a sequence of samples. I'm not trying to say what is the probability of A, what is the probability of B, and so on. I'm not trying to say what is the probability of things that appeared once or twice. I'm just trying to say, give me the multiset of probabilities. Okay. Without caring about the association. So, so the first question that we could ask about this is actually this result. The results I'm going to describe now were done earlier. So these were with Krishna Vishwanathan and Prasad Santanam and Hirakendu Das. Worked a lot on these things. And actually Jayadev as well on later results, and Shengjun Han. So this is at a time a period where we had more time to write keynote slides and so on. So more animation. Okay. Okay. So this is what we're trying to do. So the first question you'd ask is, who cares? I'm going to gamble on a horse. I want to know the probability that this particular horse wins. This particular horse wins. I don't care that one horse has probability 0.5 and one horse probably 0.3 without knowing which horse has what probability, right? So the first question to ask is, why should we even care about this? Okay, so maybe I'll give you a couple of reasons to care. So, population estimation. A lot of people care about the number of species in a habitat, okay? So this will be the cardinality of the set. So the cardinality of the set doesn't depend on the association, that just depends on the set. So that's one, or the number of mutations and so on. So for example, sensors, what happens is that you have a whole bunch of sensors in the field, and then you try to estimate how many of them are alive. So you see each one comes to life, each one signals at some point, and then you've seen maybe 7 of them, but you know that there are more, and you try to estimate what is the actual population there, even things that you're not. Coverage. So I've actually given this talk, and the guy came up and he said that he works for a company that designs drugs. It's in the Bay Area, so you never know what kind of drugs. But they're trying to. What they do is they take some compounds that they know are useful, they mix them up and they get something, and at some point they'll start getting repetitions of the compounds. So they'll get 5 different molecules or something, and they'll get some new molecule and they test it, and then they'll do it again and they'll get a new one. But at some point they'll start getting many repetitions, and they want to know when they've seen, let's say, 90% of the different combinations that they're ever going to see. That depends on just these probabilities. It doesn't depend on what has what. Or robustness. You're trying to design a system, like a wireless system for cell phones, that will accommodate people 90% of the time. 99% of the time, or road that will accommodate people 99% of the time. You don't. So what you care about is what are the probabilities that people use the system at any given time. You don't care who has what probability. You just care about there's a person who uses the system 50% of the time, another person 30% of the time, and so on. So it's just a function of the multiset. Okay. And then also security, maybe you don't care about whom, but you just want to know what's the probability that you'll see an unlikely event. Or information theory, we shouldn't even be asking this question because we care a lot about entropy. It's just a function of that. So if you're asking this question, you're not in information theory. In statistics, that's all you care about. So the answer to the question is who cares. The answer to the question who cares is that everyone cares. Okay. So just to understand it, and there'll be a little bit of repetition here because of what we have discussed last time, so I'll go over this a little quickly. So to see this, so imagine that we get visitors, and what we hear is this sequence of symbols, so at and pound and so on, 60 ats and 40 pounds. Let's assume these people are so unsophisticated that these symbols are IID. They have no structural language like some of us. And so if you analyze this, assuming independence, then you'll say how many symbols are in Motionese? 2, very reasonable, right? And what are the probabilities of the 2 symbols? 60%, 40%. So, and notice we're not saying which, we're just saying they have 2 symbols, one is probability 6, one probability 4. Okay, so this is the multiset, okay? And what method did we use? So we used the method we described last time, which is empirical frequency, right? Just use empirical frequency. But we want to sound a little more sophisticated today, so we call it maximum likelihood, okay? So what is maximum likelihood? So maximum likelihood is we're looking for a distribution. We observe some sequence X, and what we're looking is for a distribution that explains what we have seen. So we're looking for a distribution that will give the highest probability to the sequence we observed. Okay. So in this case, we saw 60 ats and 40 pounds. So we get the probability, let's say we call it P, and then 1 minus P. So the probability of the sequence is P to the 60 times 1 minus P to the 40. And if we want to maximize, we want to find a P that will maximize this. It will give us that P is 0.6. Okay? So just maximize this. And so that says that in this case, if you wanted to assign the values, you could say probability of pound is 0.4, probability of is 0.6, but we don't care about this. We just care that the probability is 0.6, 0.4. Okay. So it's easy to show that maximum likelihood always agrees with empirical frequency. So always. So for example, we see 20 of one symbol, 50 of one, and 30 of the other. Then maximum likelihood. Try to maximize the probability of P to the 20 times Q to the 50 times R to the 30. P plus Q plus R is 1. And give you 0.2, 0.5, 0.3. So, and we'll always sort them. So we'll always write it down. Okay. So as we see, it works well for a small alphabet. Like here, alphabet of size 2, 100 samples works well. This is very reasonable. But as we're going to see now, it will work very poorly when the alphabet is large. So to see that, let's assume we have not different visitors, and they speak not more Chinese, but so they speak more Chinese. So let's say someone sits here, came from China, and they write a note, and this is what the note says. Okay. Anyone can explain? No? Yeah.
Okay, this lecture is very boring, but please laugh.
So reasonably likely, because the alphabet is sufficiently large, if you see 100 symbols, all of them will be distinct. That's a very reasonable assumption. So if you try to do maximum likelihood on the sequence, then what would you get the alphabet size to be? 100, right? Because it will agree with empirical frequency. And each symbol will have probability according to this will be 1%, right? 1%. Okay, so this is very clearly not working, right? It's a very poor model, because if I hear someone speaks and every symbol is different, I'm not going to say, if I heard them 100, I'm not going to say their vocabulary is size 100. Okay, so this empirical frequency breaks down here. And what would be a better what would be a better assumption here, a better conclusion here, I should say? That the alphabet is very large, right? Maybe infinite, because if the alphabet was infinite, then it would explain why every symbol was different. Okay, so it better explains it. So large, maybe infinite alphabet. Okay. Good. All right, so let's do a thought experiment and say that we're not looking at the probability of each of those symbols, which I don't know. I don't know almost none of these symbols, so I'm not looking for the probability. I don't care. What I care about is the multiset of probabilities. Okay? So I don't care about the values. So what we can do is consider what we call the pattern. So the pattern will say, we'll just replace those by numbers. Okay, so ignore this. So what is the pattern? So the pattern is the first symbol, I say call it 1, and then 2, and so on. So in this case, the pattern is going to be 1 up to 100. Is that clear? So the first symbol I see is 1, and then the second one 2, and so on. If I saw ABA, the pattern would be 1 to 1. But here I saw ABC, the pattern is 1 to 3 up to 100. And that just signifies that all of them are different. Okay? So now I can ask, this is my pattern. Sufficient statistic for me for what I want, which is just the collection of the multiset, not the probability of each one. Which distribution will maximize the probability that if I take 100 samples, the pattern will be 1 up to 100, namely all of them will be different? The answer is exactly this. It's exactly that a large and possibly infinite alphabet will maximize the probability that all of them will be different. In other words, that the pattern will be 1 up to 100. Everyone agrees with that? Yes? Yes. Okay. All right. So what we want to do is we want to see to compare the performance of this pattern maximum likelihood to sequence maximum likelihood. Okay. So we see that it's better for very large alphabet, like here the alphabet is, you can think of as infinity, but how does it perform for smaller alphabets? So how much more time do you give?
Not too sure.
Okay, no chairs. No chair, perfect. Okay. Question withdrawn. You're the chair?
No.
Oh, okay, good. Yeah. Okay, thank you. I'm nominated, self-nominated. Okay, so I just want to, because in order to explain what we do and the results we get, I need to show you how to do it. As always, we assume the sequence is independent, identically distributed, always, and it will induce a probability on the pattern. So if we denote the pattern, for example, 1 to 1, then the probability of this pattern is the probability of observing this pattern. It's the probability of all outcomes with this pattern. Okay? So we'll do as an example. So, for example, the alphabet is ABC, and equal probability, uniform. So if we have one sample, the pattern is going to be 1, right? Because the first sample we call 1. So what is the probability that we'll get 1? If I take one sample, I'll get this probability is going to be 1. Take one sample, the pattern is going to be 1. If I take two samples, what are the possible patterns? It could be 1, 1, meaning I saw the same symbols twice, or it could be 1, 2, I saw two different symbols. So it's 1, 1, 1, 2. What is the probability of 1, 1? It's the probability that I get one of these three sequences. And you can see this AA is probability 1/9 and so on, so this probability is going to be 1/3. Okay? And this just means the probability of the second is the same as the first. What is the probability of 1, 2? It's the probability of all these sequences, and we already know it has to be 2/3 because these are the only two patterns, so it's going to be 2/3. Okay, it's the probability the second is not equal to the first. Okay, so this just explains to people who don't know what the pattern is, what it is, and how we calculate the probability. Okay, so and that's, you can see the patterns are no longer distributed IID because the probability of 1, 1 is not the probability of 1 square. So what we want to do is we want to do the maximum likelihood that we did before, and on the sequence we want to do it on the pattern. Okay. So given a pattern for example 1, 2, 1, 3, we want to find the highest probability p hat, the highest probability that this pattern can get, and the distribution that achieves this. And that's it. Okay. So let's look at length 1. There's only one pattern 1, and what is the highest probability it can get? Is clearly 1. Okay. And which achieved by what? Achieved by any distribution will give it that. Okay. Everyone understand what we mean by pattern? Yeah. Okay. Let's look at length 2, and then now we have 1, 1, and 1, 2. What is the highest probability that 1, 1 can get? 1. And it's achieved by what type of distribution? Constant. Perfect. Thank you. And how about 1, 2? What is the highest probability that 1, 2 can get?
1.
And achieved by?
Uniform on the infinite.
So notice, so by large distributions, yeah. So notice some people might say a quarter, but they're thinking of coins. We're not limiting ourselves to alphabet of size 2. So we're looking at any alphabet. Okay.
It's not really, is it really achievable? It's never really achievable.
Yeah, it approaches 1. So define it as the limit. The limit of all sequences. If you allowed yourself, yeah. Okay. So actually, the way we do it is we allow ourselves some continuous distributions. So it should actually. Yeah, but just look at the limit, don't worry. Length 3, the probability of 1, 1, 1, the highest probability is 1. The highest probability of 1, 2, 3 is again 1, the same. So the first interesting one is 1, 1, 2. Okay. And that has the same probability as 1 to 1 and 1 to 2 because it's IID. Right? This means that you have the same element appeared first 2 location and different in the third location and so on. So they have the same probability. The question is what maximizes it. Okay? So this is equivalent to flipping 3 coins and getting heads and tails, for example. Okay, so this gives you the pattern. So if that happens, sequence maximum likelihood will tell you what are the probabilities. Sequence maximum, not the original, will tell you you've seen one thing you've seen twice, the other one once. You'll say probability maximum likelihood is 2/3, 1/3. Right? And the question is, what does pattern maximum likelihood give you here? Okay? And the hope is that we saw that maximum likelihood works better for infinite alphabets, which means this is the smallest possible alphabet, size 2, heads and tails. If it also works better here, for this example, unlikely, but if it worked better here, then there's some chance it works better in between. Okay, so let's calculate the highest probability that 1, 1, 2 can get. We show it's a quarter. So we show that it's at least a quarter, and then we show that it's at most a quarter. Okay. So to show it's at least a quarter, we need to give a distribution. So suppose you're flipping a fair coin, heads and tails half. What is the probability that you'll see 1, 1, 2? It's the probability of heads, tails, or tails, tails, heads. Each of them is probability 1/8, and so it's 1/4. So there is a distribution, namely a fair coin, that will give this pattern 1, 1, 2, probability 1/4. Right? If I flip a coin, the probability that I see 1, 1, 2 is 1/4. Now the question is whether there's another distribution that will give 1, 1, 2 a probability which is bigger than a quarter, maybe half. And it could be of a binary alphabet, ternary alphabet, any alphabet. So we show that no, and this is fairly easy. So the probability of 1, 1, 2, you have to sum over all possible x's of what this is, of the probability that x appears twice, and then something different appears. So p square of x times 1 minus p of x. Okay? So now once you look at it for a little bit, you can see that you can shuffle things a little bit and write px and then px times 1 minus px. When you have this, it's at most a quarter. P times 1 minus p is at most a quarter. So it's summation px times a quarter, so it's at most a quarter. So you cannot get any higher. Which distribution achieves it? Because we want to find the distribution that achieves it. To achieve it, you need to get equality here. So you need p of x times 1 minus p of x to be a quarter for every x. So you need p of x to be half for every x. So it's this distribution over 2 elements, so it's 0.5, 0.5. So what we see is that for heads and tails, sequence maximum likelihood tells you 2/3, 1/3. Okay? Pattern maximum likelihood tells you half, half. And the question is which makes more sense. Okay? And again, if we convince ourselves that 0.5, 0.5 that is more logical here, then we've shown it's more logical in the whole range. So we have some hope. Okay. So which is more logical? So remember that we are not looking for the probability of heads and probability of tails. That was yesterday. And now we're looking at just the probability multiset, p and 1 minus p. That's all we care about. Okay. So I'll give you 2 reasons why we believe that half-half is more logical. So the first reason is that we flip the coin 3 times. Okay? So if I flip the coin 4 times and I get 2 heads and 2 tails, fine, half-half. But I flip the coin 3 times, I cannot expect 1.5 heads and 1.5 tails. So I'll never say half-half. So this is impossible. And what we saw is 2 and 1, which is the closest to this. Okay? So that's one reason why we believe this is more possible, more reasonable. The second reason is that what are the possible outcomes when you flip 3 coins? Either one side will appear 3 times, for example, heads, heads, or tails, tails, or one side will appear twice and one side will appear once. Okay. Now, what we saw in this case of 112, heads, heads, 112, what we saw is this. This is what we saw. This is what we didn't see. Okay. What will better explain what we have seen. If you take a distribution that we believe half-half is a reasonable explanation. If you take anything that is different from uniform, for example, 2/3, 1/3, then that will make this more likely. It will increase the probability of the same thing. If you take 2/3, 1/3, it will increase the probability of one side appearing 3 times, which is what we have not seen. It will decrease the probability of one thing appearing twice and one thing appearing once, which was what you have seen. Okay, so anything else will decrease the probability of what you have seen, will increase the probability of what you have not seen. Yes.
So it seems that sort of all these arguments is based upon that you don't care about the meaning of heads and tails, right? So once they actually mean something, you might refer to the...
Absolutely. Absolutely. Yeah. Yeah. Right. So remember that what we're doing today is we're changing the problem a little bit to get results that are to get around the problem that you need a lot of samples. So we're seeing what problems can you do with fewer than linear number of samples. But you're right. If we're not saying this, you only will do it if you don't care about the values. And I gave you a few reasons why you might not care which is what value, right? Like coverage and so on. If you care about the individual values, that's not what you want. So this second thing also shows that half-half is more logical. So we see that for large alphabets, pattern maximum are more logical. For binary alphabet, more logical. In between, I'll show you in at most 10 minutes it's more logical. And so what we have seen is we've calculated the probability maximum likelihood of all these things, which was very easy. Right? So, and if it's too easy, then you can ask what is the highest probability of 1112. Okay? And I'm sure people here could do it, but I just have to warn you a little bit that this problem appeared not in this name, but in a different, like the same formulation, appeared in what's considered to be the hardest international math Olympiad ever. So, but we don't have, even though we don't have a session chair, I should not abuse this. Okay, so let me skip a few slides. So this was going to show you what the problem that they had and what's the connection and so on. Okay, so just give you a summary of the results that you can get. So you can show that pattern maximum likelihood always is a smooth version of sequence maximum likelihood, which is kind of nicer because when you estimate distribution, you want to smooth things typically. And you can show L infinity convergence. You can also show L1 convergence. I didn't write it here, but what you can show is that if you want to estimate the probability multiset of k elements, then roughly you need k over log k samples. So you can reduce it from k to k over log k. So you can do that. And now I didn't write, but I'll show you some results that you can get. And I should say that Greg and Paul Valiant have a method that's very closely related to this. So our maximum likelihood, pattern maximum likelihood is we look at this. We observe a pattern, and we're trying to find a distribution that will maximize the probability of this. And so this is our definition of explains this, maximize the probability. And they subsequently came up with with a related method where they look at the distribution whose expected value is what of the number of times everything appears is what you have seen. And that also has the same very similar performance to this. Okay, so you can. I'm going to skip this, but you have a whole bunch of results. If I give you a specific sequence, what will the pattern maximum likelihood look like, and so on. I just want to show you some experiments. So here's a uniform distribution of 500 symbols, and we're taking 350 samples. So we'll never be able to estimate the whole distribution because we'll never see all of those. So in this particular run, there are 2 elements appeared 6 times, and 3 elements appeared 4 times, and so on. 161 elements appeared once. If you sum the numbers, that you see that there are 242 things that appeared. Right, so 161 appear once, plus 63 elements, plus 13 elements, and so on. 242 symbols appear, but not, out of that most you could have had 350, and that means that more than half of the 500 did not appear. Okay. So if you did sequence maximum likelihood, you'll get this thing. So you'll get these are the things that appeared 6 times and 4 times and so on, up to the things that appeared once, and you get that more than half you have not seen at all. So you're missing a couple of things. You're missing big time the support size. You're missing also the fact that it's uniform. On the other hand, if you look and try and maximize the probability of what you've seen here, then you'll get this. Okay. So you get close to the number of samples, quite close, and you get the uniformity. You get here a spike, and that's because in this particular example, the things appear 6 times, 4 times. There was something funny happened. This 5 did not appear, so it thinks that there's something that has higher probability. If you repeat this experiment 12 times, you get all these things. So you can see sometimes very good, sometimes it's not so good, but always, of course, better than sequence maximum likelihood. And what I showed you was, I think, this one, the 6th best. Okay. If instead of 350 times, you double the number of samples, maybe almost a little more, 750, then the same distribution. Then if you do sequence maximum likelihood, you'll get this. So you get more samples, but still you miss a lot and still think it's not uniform. But if you use pattern maximum likelihood, you get this. If you repeat it 12 times, always the same. Okay? And you notice all these things are monotone because we just care about the multiset, so we always just draw it monotone, just sorted. Okay. And then you can do it for other things as well. Zip distributions again. Like that. So then so again, sorry, many more examples. You can use it. Second, you can use it to estimate population. So like we said, one application of this is to estimate the population of things that you observe, and there are it's particularly has been applied to estimate Shakespeare's vocabulary. This is Efron Thiested, and they try to estimate his vocabulary. In this particular case, they found a song, a poem that people thought was attributed to Shakespeare, and it had so many words and so many were new, and they were trying to see what if Shakespeare wrote it. If Shakespeare wrote a song of that length, 430 words, how many new words will appear? And they calculated that it should be about 7, and somehow they thought 7 is close to 9. So if you apply our approach, then you take Shakespeare's things that he wrote, and then you try to see, once you do that, you get distribution, and then you can try to estimate what's the probability of how many new words you'll expect if you had 430 new things, and you see that you get a result that's very close to that. Okay, and I'm showing you a little too much. And you can let's do this. So you can apply this to estimating number of new symbols. So Zipf distribution over 15,000 symbols, and you sample 30,000 times, and you want to estimate the number of new symbols. You'll see if you take, this is how many you sampled, and you take lambda times that, and how many new symbols you'll see. So if you use a method by Good and Toulmin, which is what Efron and Thiested used, then for lambda, which is less than 1, so if your sample is of size 30,000, and you say, okay, I'm going to take 15,000 things, how many new things will appear? It actually will be very accurate. But when you go beyond 30,000, if you say I'm going to take now 31,000 new things, then it diverges. Okay, and on the other hand, if you use this pattern maximum likelihood and then predict, then it behaves much more nicely. Okay, so it extends for estimating properties beyond one. And then you can apply it to other predictions, not just number of new elements and so on. And this is one sample, and this is 5 samples. So you can see in many of them, it behaves fairly well. Not always, like here, for example. It's still better than the bounds that they would get. Okay. So I think maybe I'll stop here. But what I want to say today is that sometimes you don't need to estimate all the individual probabilities of every element, and then you can reduce it from a linear number of samples to below that, like in the case of combined probabilities to actually a constant. In this case to k over log k, but also get some results that work nicely for large alphabets. And tomorrow what we're going to do is we're going to use some of these results to get some competitive behavior to show that you can use this to do things essentially as well as anyone else can. Any questions? Yeah.
So this is a high-level question. So if you think about a probability distribution for which you know the structure is that the first thing is the most likely, the monotone case. It seems that the pattern's almost like you get a multi-set, right? So there's like the most probable element, there's some highest probability, some next highest probability, some next highest probability, so on, it might be equal. Right? If you, like, is there any kind of consistency between what your results are for monotone and what they are for pattern?
So, of course, it depends on how steep the monotone is. If you're using reasonable distribution, like ZIF distribution, then even though your probabilities go monotone, they will not appear monotonically. Just think that you have, let's say 1 over I, and now I is, 200, so the difference between 1 over 200 and 1 over 201 is very small. So things actually will not be monotone. So, therefore, if what you are saying is that you're trying to come up with things, so you cannot expect, I realize I'm not answering exactly your question, but you can definitely not expect that that what you see will observe the monotone order of what you do. Now, what we described yesterday will still supposed to work because it's assumed that the distribution is monotone, but what we're saying is that it could be a strong assumption, right? Because who knows that things are monotone or not. But so in this case, you'll get something and then you'll sort it. I'm not sure because what you'll get does not obey the order, and then you sort it. It's kind of funny. So I'm not sure. I guess that's the bottom line of my answer.
If you had a choice, right? Someone said, okay, you have a choice. You could either I will give you a monotone distribution and you have to estimate it, or I will give you. You said get the multi-set, probability multi-set. Which problem would you choose? Like, I mean,
I understand. It's a very good question.
Which is more informative, or which I guess one is informative about the distribution, and the other is making the problem easier. So
I think it seems to me like if you know that the distribution is monotone, then doing what they do makes a lot more assumptions than we do here. So we say, you give me any distribution, we'll take it, and then we sort it. We made no assumption on the distribution, we just sorted it. If you know that the distribution is monotone, and the element A has higher probability than B, higher probability than C, you must use it. I mean, if you don't use this, and we don't use it, you must be losing some information. So I don't have a proof that in that case they'll work better, but because they're assuming so much structure, they must be gaining something out of it. And this is the case where they would. So probably won't use it. But it's not like I know a proof of it. This sorting is just like an artifact of like us trying to show you things in a nice way. We didn't have to sort things.
Yes. So if you give you a pattern, so how efficiently can you compute the probabilities maximizes probability?
That's a very good question. We don't know. I mean, like, we don't know of an efficient way of doing it. What we do is we use an EM algorithm. So we take some distribution, and then we try to find a distribution that will get closer and closer and closer, and that's the approach that we use to get things to get these results. Okay. We actually don't know that this always works. So while we know that the PML, that the actual distribution will give you the results that I said you can estimate with k over log k, the algorithms that we have now, we don't have a guarantee for them. If you look at Paul and Greg Valiant, then their algorithm, the performance is similar, but for their problem, they can actually have an algorithm that will achieve it. So that's the difference.
So do you know, for example, if you have enough samples, so let's say you're close enough in some sense to the redistribution that you do converge to it?
I don't know that that's the case. I don't know that that's the case.
Just building on that, do you know if the maximization problem you are solving is NP-hard?
No, I don't know. So you're trying to maximize, mind you, something over a continuous space. So it's not a discrete. We have P1, P2, they take place in Rn, and you're trying to actually just approximate. You never try to actually, even for them, they're not trying to achieve it. You try to approximate to get to within someone give you some, delta that you want to be within. So it's maybe a little different.
But is it always maximizing a polynomial?
Yes, it's always maximizing a symmetric polynomial. Yeah. And in fact, this is a very interesting problem for us, which if you solve, then you'll help us solve the algorithmic thing. So the polynomial, for example, for 112 is summation of, so it's going to be, if you have two elements, so it's p squared q plus q squared p. It's always a symmetric polynomial. Always look at all possible permutations. It's always like that, and it's always a single orbit, as they call it. So it's just like p1 to the 5, p2 to the 3, p3 to the 1, and then just a single element, just take all permutation. This is what we're doing. And one question is whether it has a unique maximum, this maximization. If you look at all the p's, and look at p1 bigger than p2, bigger than or equal to p2, p3, if there's a unique maximum. If there's a unique maximum, then of course we can say a lot about algorithm, but we don't know that. So if that had an answer, then I think it would help us a lot in getting the same type of numbers. So experimentally, it seems to work fine. It works well, this algorithm. All this stuff that I showed is using this algorithm, but to prove it, something like that would help us.